Would you expect the second electron gain enthalpy of oxygen as positive, more negative or less negative than the first? Justify your answer. Very interesting question. O minus, sorry. First you have O gas giving you O minus gas on gaining electron. This is electron affinity, the first electron affinity. And then you have O minus gaining one more electron to form oxide ion. This is second electron affinity. Is the second one more exothermic, less exothermic or even endothermic? As a matter of fact, first electron affinity. As a matter of fact, first electron affinity of oxygen is quite strongly exothermic. Oxygen loves eating away one electron and forming O minus. But always remember, you might feel very motivated to see that in this case there is a noble gas configuration. So students normally tend to feel that because oxygen is forming a noble gas configuration, it should release even more energy. Agreed, this was one factor. But don't you forget that amongst them, the most major factor is electrostatic repulsion. There was zero charge and electron came and formed O minus. So this is exothermic or negative. On the other hand, if you have O minus giving you oxide ion, this second electron has to enter O minus against the electrostatic repulsion of first electron, and this electrostatic repulsion becomes the most major factor, so much so that it becomes strongly endothermic or positive. Second electron affinity. They said, would you expect the second electron gain enthalpy of O as positive? Yes, it is expected as positive, while the first one was actually negative. And it is so positive that overall reaction, if you add up EA1 plus EA2, this also is endothermic only. First is exo, second is endo, and second is so much of endothermic that overall reaction also becomes endothermic only. It is a fact which I am sharing with you so that you can mentally arrange the level of importance. Yes, noble gas configuration is important, but more important is electrostatic attraction or repulsion. That happens to be the major contributing factor. Question number 22. What is the basic difference between the terms electron gain enthalpy and electronegativity? Electron gain enthalpy involves complete transfer of electron. If I have an isolated gaseous atom, it completely gains one electron to form an isolated gaseous ion. This delta H is called electron gain enthalpy. This is EGE, electron gain enthalpy. When we are talking about electronegativity, electronegativity just involves pulling away of a shared electron cloud towards one atom whenever two different atoms are attached to each other. So, if you have a shared electron cloud, then this shared electron cloud, if it is pulled away in one direction by one atom in preference to the other, only this feature is electronegativity. And this slight displacement does not actually create cations or anions. It creates only delta plus and delta minus charges. It is not as drastic as complete transfer of electron, which actually would lead to formation of a gaseous anion. For those who wish to compare electronegativity versus electron gain enthalpy, these are the points in case you wish to represent them on in an answer sheet. This is the way you could do this. I'm just moving aside so that you can take a screenshot and benefit from this. How would you react to the statement that the electronegativity of nitrogen on Pauling scale is 3.0 in all the nitrogen compounds? Honestly, we will not react very kindly. We would say that that would be a very gross approximation. When Pauling declared that nitrogen's electronegativity would be around 3 on Pauling scale, well, it means that nitrogen is quite electronegative, that is okay. But please understand, that nitrogen is differently hybridized also in different atoms. What does that mean? It means that, say for example, if you have ammonia. Now ammonia can be a very lovely molecule, I don't deny that. But then please understand that ammonia contains nitrogen which is sp3 hybridized. Now same nitrogen, if it appears in pyridine, just take a look. This is sp2 hybrid nitrogen. So would this nitrogen have same electronegativity as sp3 hybrid nitrogen in ammonia? No. And say if I have CH3Cn, this nitrogen is sp hybridized. So first of all, one must appreciate that the electronegativity of nitrogen keeps on changing with hybridization. Is that so? Yes. And that's all? No, that's not all. The first point is, when you see the electronegativity of nitrogen on Pauling scale, beautiful though it may be, but we have to be very clear that this is recorded on the basis of few molecules like ammonia, NF3, whatever. But at the end of the day, electronegativity is not something which is a constant entity. Electronegativity keeps on changing with, number one, hybridization. And number two, charge on the atom. What does that mean? Nitrogen atom is electronegative, that's fine. But what about, say, in case we have Na3N, we have Na plus, and we have nitride ion. Now, I hope you remember that nitride ion also contains nitrogen atoms. Can I say that the electronegativity of nitrogen in this case would be 3 on Pauling scale? No, of course not. Why? 3 refers to a neutral atom or an apparently or nearly neutral atom of nitrogen. The moment nitrogen acquires a negative charge, it becomes very quickly electron rich, and if it becomes electron rich, it rather would start releasing electrons than donating electrons. Electronegativity sharply decreases with increase in negative charge. As a matter of fact, nitrogen with -3 charge on it would be highly electropositive. It would tend to donate electrons. Why? Because it's already so rich. So electronegativity also depends on charge on the atom. As the positive charge on the atom increases, electronegativity increases. And as the negative charge on atom increases, electronegativity decreases. So 3 is a kind of very idealized value. I would not say that 3 is something which can be applied blindly absolutely anywhere. But yes, these two are the really major factors which are going to affect electronegativity as well. Describe the theory associated with the radius of an atom as it gains an electron. Now, if an atom gains an electron, please understand what happens to its nucleus. Actually, nothing happens to its nucleus. The nucleus remains the same. So, as an atom gains an electron, a number of protons in the nucleus remains the same. Yes. And then number of electrons, that means nuclear attraction. Nuclear attraction is the same. Yes. Sorry. As a matter of fact, this question has appeared before also in same NCERT, but then let me again recount it because there was the same thing probably thrice. Now, for the same nuclear attraction, you have more number of electrons because it has gained one electron. Number of electrons increases. Therefore, electronic repulsion increases. There is a concept called as effective nuclear charge, which is atomic number Z minus S, where S is the screening constant. Now, atomic number remains the same, but S increases. Why? Because there is more electronic repulsion, so more screening. Because of this reason. Because electronic repulsion increases. Therefore, effective nuclear charge is reduced. Effective nuclear charge is reduced. That means now the outermost electron feels the nuclear charge a little less. Nuclear charge is the same, but due to additional repulsions, the outermost electron experiences lesser attraction by the nuclear charge. Hence, you find that it can go a little more away or the size increases. Z effect is used, therefore, size increases. Please note, nucleus pulls the electrons inwards. If the nuclear pull inwards decreases, size increases. As simple as that. And when it comes about losing an electron, this also gets very interesting. You have an atom A. If it loses an electron, again, first 2 points are the same. Nuclear charge remains the same, there is no change in the nucleus. But since electron is lost, you find Z effective, which is Z minus Z star, or sometimes people call it screening constant S also. S. So, if electrons are lost, means lesser repulsion. Therefore, S decreases. Therefore, Z effective increases. Effective nuclear charge has increased. It means that electrons are now experiencing greater attraction by the nucleus because the repulsion between themselves has gone down. If they are attracted more, they are sucked in, they are pulled in, and the size decreases. Therefore, atomic radius decreases. As simple as that. Would you expect the first ionization enthalpies for two isotopes of the same element to be same or different? We would expect ionization enthalpies to be the same. Justify your answer. That's very simple. See, ionization energy depends on the net force of attraction which is exerted by the nucleus on the outermost or the most loosely bound electron, right? So, we need to see Z effective, which is Z minus S. Z is the actual number of protons in the nucleus, and S is the so-called screening constant, which reflects the repulsion by the inner electrons which are trying to push the outermost electron out. Fine. Now, Z is nuclear charge, right? This depends on number of protons, and number of protons in both the isotopes is the same. S depends on electronic configuration and number of electrons, which is again same for isotopes. For isotopes, atomic number is the same and screening constant is the same. So, effective nuclear charge also is the same. And if isotopes have same effective nuclear charge, it means that they are attracting the outermost electron to the same extent, and that is why they have the same ionization energy. That's it. What are the major differences between metals and non-metals? Oh my God, this is an ancient question. You have been studying this since, I don't know whenever you started studying, right? And probably many lifetimes all over. See, the differences are numerous. First of all, metals are metals. What does that mean? Metals are usually solid at room temperature, barring very few ones. Like if you take 25 degrees Celsius, 1 atmosphere, mercury is the only metal which is liquid. Otherwise, if you increase the temperature a little, cesium, francium, maybe rubidium and even gallium can turn liquid. But otherwise, most of the remaining metals are solids at room temperature. While non-metals could be just anything. They could be solid, they could be liquid, they could be even gaseous. Absolutely any state would be applicable. Metals are usually malleable and ductile. What is malleable? If you beat them, you can make very thin sheets out of metals. If you beat non-metals like carbon, can you make very thin sheets of carbon? No, sorry, you can't. You might be able to make thin sheets of carbons by some other method, but not by beating carbon. It is brittle, it is going to break. So non-metals are not malleable, they are rather brittle. They will break if you beat them by a hammer. Metals are also ductile. If you want to draw them, you can draw them into thin wires. Non-metals are not ductile. You cannot have wires of sulfur or wires of carbon. That is absurd. You don't have them. Sorry. Metals are usually good conductors of heat and electricity. Actually, they are always good conductors of heat and electricity. What about non-metals? Non-metals are usually poor conductors of heat and electricity. There are notable exceptions like diamond is an excellent conductor of heat. On the other hand, graphite is a very good conductor of electricity. But then, these are rare exceptions. Otherwise, usually non-metals are poor conductors of heat and electricity, while metals are always good conductors of heat and electricity. Metals are sonorous. They possess a metallic luster or shine. Sonorous means they have a kind of clinging sound when they strike each other. Like when you strike a bell, there is a sound, tang, but then, or there is tinkling of coins or something. You don't have similar sounds by non-metals. They are not sonorous and they are not as lustrous as metals often, usually. Then metals generally form cations. Is it? Why? Because they are electropositive. Non-metals generally tend to form anions because they are electronegative. We can just go on, but these are some of the most representative and classic characteristics of metals and non-metals. I'll just move myself aside so that you can copy if you wish. And this is the theory you need. Take a screenshot if you desire. Use the periodic table to answer the following questions. Okay. Identify an element with 5 electrons in the outer subshell. Well, 5 electrons in the outer subshell. That would be group 5, right? Yes. So that would be group 5. Group 15 should be the one you should consider. 15 is the group. So if you have nitrogen, phosphorus, arsenic, antimony and bismuth, they have 5 valence electrons. NS2, NP3, a total of 5. That is the valence shell configuration. Don't look at this. Don't look at these. These are bad numbers. And NCERT is not very sublime. It is one table directly copied from NCERT, but then they are not very good when it comes to numbering them properly. Identify the element that would tend to lose 2 electrons. Which element would tend to lose 2 electrons? If after losing 2 electrons, it becomes, it acquires noble gas configuration. Actually, group 2 elements are the ones which would tend to lose 2 electrons. So you have beryllium, magnesium, calcium, strontium, barium and radium. These are the elements which would form dipositive cations. They would tend to lose 2 electrons. Right? There we are. Interestingly, you also have more. Group 2b, if you see, or zinc, cadmium, mercury. This is again one group which also loves to lose 2 electrons and it also forms dipositive cations. Identify the element that would tend to gain 2 electrons. If by gaining 2 electrons they can acquire noble gas configuration, that would be lovely. And this means that we are talking about group 16. These are the elements. Skip polonium. Polonium being a metal, it can have its own issues. But oxygen, sulfur, selenium and tellurium, this is a group 16, which contains, yes, non-metals, and these non-metals or metalloids would very much love to gain 2 electrons like this. Now, this is very interesting. If you look at it, you need a metal and a non-metal both, liquid as well as a gas both. If you care to see, group 1 has a metal, the full group is metals, lithium, right till cesium. You also have a non-metal, hydrogen. Is there a gas? Yes, hydrogen is a gas. But if you look at others are solids, there is no liquid. So group 1 would not qualify here. Other than group 1, if you look at S, D or F blocks, the entire block contains metals, and metals alone, you would not have non-metals. So the only place you can look at would be P block. In P block, if you want a liquid, now gaseous state is pretty popular. Solid state is very popular, of course. Liquids are not so common. If you look at group 13, all of them are solids. Group 14, all are solids. Gases begin from group 15. Yes, you have nitrogen, which is gaseous. Then you have phosphorus onwards, solids. In group 16, you have oxygen, which is gaseous. Sulfur onwards, they are solids. If you look at noble gases, all of them are by name itself gases. Liquid is present only in one family, my dear, and that is halogens. Bromine is liquid at room temperature. Fluorine and chlorine are gaseous at room temperature, while iodine is a solid. Okay. What about metals and non-metals? Honestly speaking, if you just look at the first elements F, Cl, Br and I, the first 4 are very much non-metals. F, Cl, Br and I are non-metals. Astatine, At, is a metalloid, and Ts is something, 117, the very elusive element, that is supposed to be a metal. So yes, you have indeed, although radioactive and very unstable and rare, you have metalloid, you have you have lots of non-metals, and you also have a metal. That, my dears, would be the only group which would qualify for this. One warning before we go ahead. Many of the popular internet solutions with very famous companies mention iodine as metal. That is absolutely absurd. Iodine is a classic non-metal. If you want, you just look at the solutions provided by other internet companies, edtechs, you would mostly discover that they have copied it from each other and they are declaring iodine as a non-metal, iodine as a metal, which is quite gross. It is not. Just because many people are saying it, please don't confuse that, because 10 people are writing it, it's correct. Also note that every comma, full stop is copied. So they're just copies from each other, copied by bots and robots, not even technically or by some sensible persons, right? Fine. This is it. Increasing order of reactivity in group 1 is lithium, sodium, potassium, rubidium, cesium. Down the group, reactivity increases. On the other hand, if you look at halogens, it is the reverse. Fluorine is super halogen, very reactive, and Cl, Br and I are successively less and less reactive. We are supposed to explain this. Why? It's very simple. If you look at metals, when we are moving down the group from lithium, sodium, potassium, rubidium, cesium, you discover that on moving down the group, metals typically react by losing electrons. So, lithium to cesium, the tendency to lose electrons increases. So, electropositivity increases down the group. Why? Because as you go down the group, ionization energy decreases. It becomes easier to lose electrons, so it becomes easier to react. So that is why reactivity increases down the group in alkali metals. If you look at halogens, the scene is very different, because when you talk about halogens, halogens typically are electronegative, right? If they are electronegative and you find, that means they are not going to release electrons, they would rather accept electrons. So, tendency to accept electrons decreases down the group as the size increases. But then electron affinity has an exception also. Chlorine is more electron, it has greater electron affinity as compared to fluorine. That's okay. But again, a very major tendency in these cases is, of course, electronegativity. negativity decreases also down the group as the size increases. And the most important factor is the bond length. Bond length increases. Therefore, bonds become weaker, with therefore lesser energy is released during bond formation if you are moving down the group. So when it comes to covalent bonds, you find lesser and lesser energy is released if you are moving down the group. That is why reactivity decreases. And if you are talking about ionic compounds, then small anion F minus will give you a higher lattice energy. Higher lattice energy again means higher reactivity. So may it be ionic or may it be covalent, halogens, amongst halogens, fluorine is the most reactive. Why? Because it has highest electronegativity, easy. FF bond can break very easily. It has very low bond dissociation enthalpy. It forms very strong bonds and it has very high lattice energy as well. So all these things contribute to relatively higher reactivity of F as compared to Cl or Br or I. Right? Write the general outer electronic configuration of S, P, D and F block elements. That's not very difficult. Amongst S block elements, you have NS1 and NS2. So sometimes people write it NS1 to 2. That is the general configuration. This is group 1 and this is group 2. In P block, outermost configuration is NS2, NP1 to 6. Like group 13 is NS2, NP1, and group 18 is NS2, NP6, and in between you have NP1, NP2, NP3, NP4, NP5, NP6. This is the variable part which has been covered here generally. NP1 to 6, that is a general outer electronic configuration of P block. If you look at D block, it gets more interesting. This is NS2, N minus 1, D1 to 10. NS2, ND1, N minus 1, D1, NS2 to N minus 1, D10, NS2. This is usually an electronic configuration of D block. There are rare exceptions. Sometimes it becomes NS1, and that too for groups like group 6 and group 11. That's fine. So for group 6, you have N minus 1, D5, NS1. And for group 11, you have N minus 1, D10, NS1. Extra stability of half-filled and fully filled atomic orbitals change their general configuration, and you have NS1 instead of NS2. But other than group 6 and group 11, this is the common configuration of D block. And for 6 and 11, these are the configurations generally. What about F block? F block is N minus 2, F 1 to 14. Okay, very interesting. NS2. Is that so? Yes. Okay. So, and what about D block? D block comes later on, or sometimes in rare exceptions it does appear, but this is typically the case. So it's something like 4F14, 6S2, 4F1, 6S2. This is how it begins, and this is how it carries forward. That, my dear, is your F block generally. So if you summarize all this, this is what you get. For S block, NS 1 to 2, P, NS2, NP 1 to 6, D block, N minus 1, D, and D can vary from 1 to 10, NS, now NS could be 0 in rare case like palladium. It could be 1 also in rare cases like copper or chromium or silver or gold or molybdenum or tungsten, something like that. And generally it is NS2. And what about F block elements? F block elements have typically n minus 2. F could be, 0 to 14, whatever, है ना? But at the same time, rarely in D block also, like after lanthanum, when you have cerium, cerium goes to, n minus 1, D1, NS2 that way. So yes, it could be that way, है ना? So D can be 0 or 1 sometimes, and S is always 2, NS2. Yes. These are the general configurations of SPD or F block elements. Assign the position of the element having outer electronic configuration NS2 NP4 for n is equal to 3. Okay. N is equal to 3, that means 3s2, 3p4. That means if n is equal to 3, it belongs to third period, and 3s2, 3p4, that means outermost shell contains 6 electrons. It has group 16. So this is sulfur. Sulfur, this is third period and 16th group. How do you infer that? It is a p block element, because outermost electron is in p subshell, so it is a p block element. And overall valence shell contains how many? 2 plus 4 is equal to 6. Therefore, within p block, 6 plus 10, that makes it 16th group. So this is a 16th group element. The next one says n minus 1 D2 NS2. Very interesting for n is equal to 4. That means I have 4s2, 3d2. At the moment I have d2 configuration, please understand D block begins from group 3. So this is 2 plus 2 is equal to 4. Therefore, it is a fourth group element. It is a fourth group element, and since n is equal to fourth, it is a fourth period element also. Fourth group, fourth period, we are talking about the loveliest, titanium. Titanium is the element they are talking about. And what about this n minus 1, F7 n minus 1 D1 for n is equal to 6 in the periodic table? This sounds even more exciting. You have 6s2, so it is 6th period. Excellent. It is F subshell. If it is F subshell, that means F subshell is entirely in third group. So they are talking about third group. It is 6th period and third group. And now F7 n minus 1 D1 NS2. It's very typical. You are talking about, this is 5D1 and 4F7. So you're talking about gadolinium GD. This is GD. I mean the 7th element of lanthanide series, and this one has this configuration. The first delta H ionization and the second ionization energies and the electron gain enthalpies of few elements are given below. Lovely, I'm given some data. Okay. Which of the above elements is likely to be A, the least reactive element? Now, when we are talking about electron gain enthalpy, you should feel happy while gaining electrons, right? Even alkali metals, the very donor ones also, they feel okay. They release some energy if you give them electrons. All negative. Now this is ugly, because do you see that you have to really push in energy. You're giving electron, that is big deal itself, and you also have to supply energy. And not just withstanding that, they have an insanely high value of ionization energy as well. So they have worst ionization energies. That means it is very difficult to take electrons away from them, and they have very poor electron affinity. That means they don't even like accepting electrons. This is ridiculous. Now you don't want to accept electrons, you don't want to give electrons, then what do you want? You want to do nothing. Yes, they are saying we want to do nothing. So that means the least reactive is 5. They are very seemingly noble gases or something of that kind. 5 appears to be the stupidest of all, and yes, it is. B part, the most reactive metal. Now they are talking about metal. Metals are likely to have very less ionization energies. The less ionization energies are these and these. And the least is this. You see that? So we have nothing to do with electron affinities simply because we don't expect them to be having good electron affinities. Metals are not happy accepting electrons. And anyway, these three are poor ones, so they are a kind of proof that these are metals. They have low ionization energies and they also have low electron affinities, so albeit exothermic. Most reactive of these metals seems to be 2. Why? 2 has lowest ionization energy. That means it can give away electrons most easily. That means it will react most happily. Makes sense for me. Fine. Most reactive non-metal is going to be something which accepts electrons very happily. Now, happiness while accepting electrons can be seen here. Now, ionization energy is high. Who cares? We are not going to ionize them anyways. So they may keep having high ionization energy. 3 happens to be a non-metal as well as 4. Both of these are non-metals. And amongst them, more energy is released by 3. That means 3 is a more reactive non-metal, most probably. Is that the only criteria? Actually, that is not the only criteria, because for that matter, electron affinity of chlorine is even greater than that of fluorine. Although fluorine happens to be more reactive. But then based on this data, this seems to be the only thing which we might be able to infer, unless we remember what are the exact values of electron affinities of F and Cl. Just let's wait for a moment. Just observe this also. This has high electron affinity. This also has high ionization energy. Had this been fluorine, now fluorine would have a high ionization energy as compared to chlorine. No, and this one seems to be having less. So there is no case or no fear of exception of F and Cl here. 3 happens to be most reactive, and that makes absolute sense. Least reactive non-metal. Actually, there are only 2 non-metals. In fact, least reactive non-metal is 5. Why? 5 is a noble gas, and all noble gases are non-metals. So yes, that is the least reactive non-metal indeed. The metal which can form a stable binary halide of formula Mx2. Now they are looking for a metal which has a formula Mx2. If I look at these 3 candidates, they are metals. They are metals, right? And the other three are non-metals. So I am not even considering them. These, they are non-metals. So I am not talking about them. Fine. Amongst these 3, see, 520 is the energy which is required to remove the first electron. The second one, if you remove, it is more than even 10 times, more than 5,200 also. That means removal of second electron is very difficult. That means most probably one forms only +1 cations, not +2. In second case, please note 419 and 3051. This is also, if you just care to note, it's roughly 7.5 times more, 700% more, which is like very high. So this most probably 2 also is going to form +1 cations only. Why? Because removal of second electrons is like, second electron is quite difficult in case of both 1 as well as 2. If you look at 6, 738, and it is just twice. Anyway, second energy must be more than first, that's okay. But it's not like 10 times or 8 times or 5 times, nothing like that. This appears more humane. That means it is losing second electron reasonably happily. So I would say that 6 would be most likely to have this formula Mx2. It would also show a valency of 2 instead of 1. Metal number 1 and 2, they would have valency of 1 only. Metal number 6 will have valency of 2. The metal which can form predominantly stable covalent halide of the formula. Okay, if the metal has to form a covalent halide of formula Mx, first of all it must have valency 1. If it has valency 1, it has to be either 1 or 2. Okay, and it can form a predominantly stable covalent halide. Now, if it has to form a covalent halide, that means it must have more polarizing power. More polarizing power means higher ionization energy. Now, 1 seems to have higher ionization energy. That means more polarizing power, also more covalent compound. So, the best answer would be 1 in this case. Very instructive, beautiful question, deeply conceptual. Predict the formulas of stable binary compounds that would be formed by the combination of the following pairs of elements. And we have first lithium and oxygen. Well, lithium would be +1 and oxygen is -2. Oh wow, so what do? Yeah, magnesium. Magnesium is +2 and nitrogen is -3. Fabulous. So what happens? You just cross multiply. Okay, Charan exchange, yes. And you have Li2O and you have Mg3N2. These are the stable binary compounds formed by these combinations. Aluminium and iodine. Aluminium is +3 and iodine is -1. Silicon has a valency of 4 and oxygen -2. What happens? Again, Charan exchange. So we write Ali3 and we write Si2O4. No. Whenever there is a common number, we cancel it. So divided by 2. So we have SiO2. This is correct. If they have a common factor, simply cancel it out. We just take the ratio, that's all. Phosphorus and fluorine. Phosphorus goes to +5 as well as +3. Phosphorus shows a variable valency and fluorine shows just -1. Element 71 and fluorine. Now this gets even more interesting. You would need to locate where exactly is element 71. I would recommend that you remember the atomic numbers of noble gases. Like xenon is 54 and radon is 86. So if xenon is 54 and radon is 86, it has to be somewhere in the 6th period. Xenon is 5th period. At the end of the 5th period, it has to be after that, that means 6th period. And element 71 would be somewhere in 6th period. Now, 71. Now, please note, after xenon, what do you get? You get cesium, which is 55. Right? And after cesium, what do you get? You get, barium, which is 56. That's very lovely. But what about 71? Now, 56 plus 10 would give you 66 plus 5 more. So, 56 plus 15 gives you 71. Can you locate where exactly in periodic table would this be? And that, my dear, would be the end of F block. End of F block, yes. See, you have 55, 56 as barium, and then you have 57 as lanthanum. You add 14. Now 58 till 71 would be F block. So lutetium is what we are referring to here. It is an F block element, yes. And all F block elements typically have a valency of 3. So lutetium would have a valency of 3 and F minus. Wow, this is the case. Yes, dears, this is the case. And now Charan exchange. So you have PF5 and you also have PF3. Lovely. What about here? You have LuF3. Lutetium fluoride, LuF3. Just check this out. And in this case, you also had an additional responsibility of actually identifying the element, which makes it more interesting. In the modern periodic table, the period indicates the value of nth period means principal quantum number. Yes. So it is principal quantum number. Which of the following statements related to the modern periodic table is incorrect? A. The p block has 6 columns because of maximum of 6 electrons can occupy all the orbitals in a p subshell. That is correct. Very true. So this is correct. So this, and we have to choose incorrect. So don't get confused. The D block has 8 columns. No, that is wrong. D block has 10 columns because a maximum of 8 electrons can occupy D subshell. This is wrong. This is incorrect. Each block contains a number of columns equal to the number of electrons that can occupy that subshell. This is correct. This is true. And the block indicates value of azimuthal quantum number L for the last subshell that received electrons in building up electronic configuration. Yes, that is why we have S block, P block, T block and F block. This is also true. So true, truth is not valued here. This is Kali Yuga. So this is incorrect. B is the answer. Yes, B is the answer. Anything that influences the valence electrons will affect the chemistry of element. Yes. Which one of the following factors does not affect the valence shell? Okay. The valence principal quantum number N, obviously that would affect the valence shell. The nuclear charge Z, okay, that would affect the valence shell. Nuclear mass. Now nuclear mass includes nuclear charge as well as the number of neutrons. Number of neutrons is not something which actually bothers the valence shell really, and the number of core electrons, that yes does affect valence shell because that affects the screening constant, and yes, Z effective is controlled by core electrons. Also, nuclear mass is something which is irrelevant. I repeat, when you are comparing isotopes, they have same electronic configuration and virtually same properties, largely because number of neutrons variation actually does not affect the properties of a given element. The size of an isoelectronic species, F- neon and sodium ions, is affected by, well, A, nuclear charge. Is the size affected by nuclear charge? Yes, it is. Valence principal quantum number N, it is same for each of them. Electron-electron interaction in the outer orbitals, it is same for each of them, and none of the factors because their size is same, that is wrong. Nuclear charge is the key for comparing size of these isoelectronic species. Each of them contains 10 electrons, please note. Which of the following statements is incorrect in relation to ionization enthalpy? 1. Ionization enthalpy increases for each successive electron. That is not correct. It usually increases, but then there are cases when it dips down. So it is often true, but not always. Let's take the next option. The greatest increase in ionization enthalpy is experienced on removal of electron from core of noble gas configuration. This is very correct. B is correct. So that is not, I'm not saying it's the answer, I'm saying it's correct because we have to choose the incorrect statement. End of valence electrons is marked by a big jump in ionization enthalpy. Yes, because valence shell, once it is complete, if you try to break it, it is a very huge ionization process. So yeah, this is true. They are not the answers, I repeat. Removal of electron from orbitals bearing lower n value is easier than orbitals having higher n value. Now this is a really bad idea. If you're removing lower n value, if you're removing inner electrons and they're saying it is easier. No, it is not easier. It is more difficult because the lower n values are being attracted more strongly. So this is absolutely false. This is often true. So if you're talking about incorrect, truth is, if the question comes under the heading, choose only one answer, I would say D is the answer. Considering the elements boron, aluminium, magnesium and potassium, the correct order of the metallic character is, now most metallic is group 1, then group 2, then group 3. And boron is a non-metal, aluminium is a metal, so obviously boron is poorer. So boron has to be poorest of all, yes. Potassium, magnesium, aluminum, boron. This is group 1, group 2, group 3. And in group 3, down the group, metallic character increases. So that is the fact which we use for determining the order of metallic characters. Considering boron, carbon, nitrogen, fluorine and silicon, the order of non-metallic character is non-metallic character. It increases across the period. and it decreases down the group. So least metallic and most non-metallic is fluorine. Fluorine is most non-metallic. Then comes nitrogen, then carbon. This is correct. Nitrogen and carbon. Now, if the competition is between boron and silicon, please note carbon, then you have boron and you have silicon here. Yes. The way it is traveling like this, you find that non-metallic character increases here. Yes. And non-metallic character also it decreases here because metallic character increases here. So carbon is a better non-metal, more non-metallic than silicon as well as boron. How do we compare boron and silicon? Down the group, it is more drastic change as compared to across the period. So silicon is a metalloid, sometimes it is said. Boron is a classical non-metal. So boron would be more non-metallic as compared to silicon. Yes. So is C the answer? Very much. I hope you can see. C is the answer. Considering F, Cl, O and N, the correct order of the chemical reactivity in terms of oxidizing property is, oh my God, fluorine is most amazing when it comes to reactivity. So yes, fluorine happens to be the best. So C and D are instantaneously out. Stupidest is nitrogen. It is least reactive amongst them. So yes, it is also there. Between oxygen and chlorine, if you're talking about the oxidizing power, which has greater oxidizing power, chlorine tends to have a slightly stronger oxidizing power. They are very clear in terms of oxidizing property. So A is the answer. Yes, A is the answer. So my dears, this was the periodic table of elements for you, NCERT Solutions, the classic ones. I'm sure if you refer to them, you're not just going to learn the solutions, but you're also, you're going to have some insights into the theory of this great chapter of periodic table, which is fundamentally crucial as well as very, very necessary. All the best. Stay tuned with us and keep watching us at Vyas Edification for such high quality good solutions. Bye-bye. Keep learning. Have a great time.